Okay, chapter 11, infinite sequences and series. Okay, so if you've never seen anything about sequences and series before, please go over to my pre-calculus videos, and somewhere toward the end I do a more thorough introduction to what sequences and series are. Here I'm assuming people have already done a little bit of work with sequences and series, so hopefully things will go kind of smoothly. If not, go over there and get yourself familiarized with sequences and series. Okay, so what is a sequence? A sequence can be thought of as a list of numbers written in a definite order. Okay, so it's any list of numbers. The actual values can be anything. The only thing that is unique about these is that the order matters, right? So, for example, we could just have, say, 2, 4, 8, 16, 16, 32, and so on and so forth. So here's a list, which happens to be powers of 2. And what matters is that the order of the list matters, right? This is the first one on my list. This is the second one on my list. This is the third one, the fourth one, the fifth one, and so on and so forth and so on and so forth, right? So we're only dealing with lists that go on forever, right? So here is one potential sequence. Another one could be something like 20, 19, 18, 17, 16, dot, 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 dot. And again, the order is what matters. So this is the first one on my list, the second one on my list, the third one on my list, the fourth one on my list, the fifth one on my list, and so on and so forth. Okay, so any values at all. They don't have to have any specific reasoning, right? It could be randomness. It could be that the first number is 7.2 and the second number is negative 4.5 and the third number is 0.2 and the next number is 111, right? So there doesn't have to be like a good reason for it. It could be that they're assigned sort of randomly, and that's still a sequence, right? As long as this goes on forever, it doesn't have to be a pattern. Of course, if there is no pattern, then it's not as interesting, right? So we're only really interested in cases where we can establish some sort of pattern, some sort of way of describing it. Although there are many sort of real-world situations where we draw these values, maybe something from outer space or something, some values we're detecting. It could be something microscopic, right? Something about electrons and their position with relation to the center, all kinds of stuff this could be. And there might be a pattern, and hopefully there is. That's when things are interesting, or there might not be. But for our purposes, they mostly have patterns, right? That's the interesting thing. So some sort of a list of numbers. The order is important, and they go on forever. Okay, so right here. So the number a sub 1 is called the first term, a sub 2 the second term, and in general, a sub n is the nth term. We will deal exclusively with infinite sequences such that so each term a sub n will have a successor a sub n plus 1, right? So there's always going to be a next one. So back to this thing. So we call, the first one here, in terms of that notation, that's a sub 1. And this value there, that one's a sub 2. And dot, 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 dot. Somewhere over here, we'll have the a sub nth value 1. And right next to it will be the a sub n plus 1 value. Good. And then these go on forever. So they don't stop at n. They just keep going. Forever and ever. Okay, notice that for each positive integer n, there is a corresponding number a sub n, and so the sequence can be defined as a function whose domain is the set of positive integers. We also refer to that as saying that it's a list of numbers that is indexed by the counting numbers, right? So it's the first one, the second one, the third one on the list, right? So we can also think of a function such that when I input, some value, here's some function, blank, some function, and then, there's an input-output. So I input a 2 to indicate this value here, and the output is going to be 4, right? So it's a function whose domain is the counting numbers, and the output is the values on my function. Good. So now instead, if I input a 5, I should get a 32, right? So if this function exists, then it would be a function that describes this particular sequence. So notation is really important. There's lots of different ways to describe a sequence. So let's cover a few of the ways in which we can do that. Okay, so notice that for every positive integer n, there is a corresponding number a sub n, and so a sequence can be defined as a function whose domain is the set of positive integers, but we usually write a sub n instead of the function notation f of n for the value of the function at the nth number. Okay, so here's one way to describe a sequence: a sub 1, a sub 2, a sub 3, dot, 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 dot. Or just these, curly bracket, a sub n, curly bracket. Or we also might describe the beginning of n. Now, normally n begins at 1. It's the most common thing, but it doesn't have to. So it could be a sequence where the first value begins at n equals to 2 or n equals to 3 or something like that. Good. Okay, so here's more examples of sequences and how we can describe them. So here's one way to describe it. It's the formula, n over n plus 1, and then it goes from starting at n equals to 1 out to infinity. Remember that the inputs are the location on the list, and you can't have a decimal location on a list. It's either the first one on the list, the second one, or the third one. It can't be the 1.02th one on the list. So in this context, it doesn't make sense for the input values to be decimals, right? So the input values are only counting numbers, whatever they are. So here's one way to describe it. Here's another way to describe it. There should be like a little separator here. Right, here's another way to describe it, like this, and then another way to describe it. And then really another way to describe it would be to use function notation. F of n equals to n over n plus 1, right? And remember, n refers to the location on the list. So when n equals to 1, let's put it over here. N equals to 1, then it's the first one on the list. Oh, you know what? Actually, I don't want to write it like that. Let's do. When n equals 1, then we have 1 over 1 plus 1, and then this is the first one on my list, comma. When n equals to 2, then we end up with 2 over 2 plus 1, which then becomes the second one on my list, and then 3 over 3 plus 1, which becomes the third one on my list, right? Dot, 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 dot. And so n over n plus 1 is the a sub nth one on my list. And just to be clear, the one right after that would then be n plus 1 over n plus 1 plus 1. Right? Maybe I should have put these in color. Let's put these in color. Okay, so this one was when n equals to 1, we had 1 over 1. When n equals to 2, we have 2, and 2 over 1, 2 over 2 plus 1. Then when n equals to 3, we had 3 over, oh, that's supposed to be in color, 3 plus 1. And then out to n, so this would be n over n plus 1. And then the one right next to it would be n plus 1 over n plus 1 plus 1. Right, so this would be the a sub n plus 1 term, the one right after it. Right, and this is when n equals to 3, dot, 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 dot. This is the nth term, and this is the n plus 1 term. Okay, So lots of different ways to do it, but keep in mind that when we write it like this, we're only looking at cases where the function has a domain of the counting numbers, right? Because n is the location on the list. It really wouldn't make sense for n to be equal to 1.2, for instance, right? There's the first one on the list, the second one on the list. There isn't a 1.2th one on the list. Good. Now, how does this relate to a function whose domain is the real numbers, right? So note that we can write f of x equals to x over x plus 1, and this is where x is all real numbers, where x is an element of the real numbers, so all real numbers. Or you can also say that well, that's probably the best way to say it. All real numbers. And that is related to this, but here the inputs are just counting numbers, right? So specific values of these are the ones we input to here, right? So let's look at a graph to point that out. So let's look at this. We'll get back to that in a second. Let's go to Desmos, desmos.com. Graphing. So f of x equals to x divided by x plus 1. Looks like that. This is where x is all real numbers, and of course we have a vertical asymptote at x equals to -1. But let's just focus on the positive, right, since we're looking at integer values, counting numbers. So that's these over here. Okay, so now if we looked at, not that table. If we looked at this, what we would have is the following. N divided by n plus 1, where this is n. And so we'd have 1 there, and then 2, and then 3, and then 4, and then 5, right? So this formula with n's, where n is just integer values, counting numbers, right, becomes these individual little dots, which are a subset of the function that has all the real numbers. Okay. So you can also point out that this guy right here is 1 comma, and then this, which ends up being 1/2. Let's see, take a picture of this. So let's put it. So these ordered pairs right here become 1, and then 1 comma 1/2. This is going to be the point 1 comma 1/2, and then 2 becomes 2 comma, and it's 2/3. That's that one. And then that one right there becomes 3. So it's 3 comma, and then be 3/4. Right? And then last one I'll put, this is 4 comma 4/5. And so on and so forth. Good. And that's what these are. All right, let's move on to the next one. So here we have a -1 to the nth power. So as n goes from 1, 2, 3, 4, the sign will alternate, right? So this is one of the most common ways in which we can express a sequence where the terms are alternating signs, positive, negative, positive, negative, positive, negative. Then we have an n plus 1, and then the whole thing divided by 3 to the power of n. So we're going to go over powers of 3 in the denominator. So this is one way to express that sequence. Here's another way to express it, right? So we should have, this is one way to express it. There's another way to express it. Again, we could do it in terms of a function notation as well, where this is f of n equals to -1 to the nth power times n plus 1 divided by 3 to the n. So this is another way to express that sequence. And then, of course, you can really make it painfully obvious by saying where n equals to 1, 2, 3, 4, dot, 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 dot. And then here's another way to express it where you begin writing down a few of the terms and dot, 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 and then you jump over to the nth term in the middle. Okay, I think that's fairly easy to follow. Here's another one, same idea. We have ourselves one way to express this. Notice that in this case, n does not start at 1. Because if we let n equal to 1, we'd end up with 1 minus 3, which is a negative, square root of a negative. We get into the imaginaries, and we don't want to do that. So this sequence is identified as starting at n equals to 3. Okay, out to infinity. That's okay. We can start at any integer value as long as this goes out to infinity. Right? We are only focusing on sequences that don't have an end. They go out to infinity. Okay, so another way of describing it is this way, and then of course there's the function notation, or this way, which we start with a few key values and then we jump over to the nth value. Okay. Last example. Okay, now in this case, n starts at 0. Not necessarily 1, it could start at 0. Okay, so then goes out to infinity. That's one way to express it. Here's another way to express the exact same thing. Right, this is the most common, popular way of doing it. And then, of course, the next one. Good. Okay, all right, let's move on. So a sequence such as the one in example 1a, a sub n equals to n over n plus 1, can be pictured either by plotting its terms on a number line, as in figure 1, or by plotting it in figure 2. Okay, so let's look at this style of presenting the graph of a sequence. You zoom in over here. So what this is doing is just graphing the values on a horizontal number line. So remember that the sequence was, let me put it over here. The sequence was a sub n equals to n over n plus 1. So when n equals to 1, it was 1 over 2. N equals to 1 was 1 over 2. So you plot this dot right here because it's at the half between 0 and 1, so that's a half. But you also have to identify that that's the first one on your list. And then the second one on our list was 2 over 3. 2/3 is going to be right here. That's like 0.67. And then 3/4, that's going to be 0.75. That's going to be this one right here. So at each point, you have to identify where the dot is on the horizontal line, and also identify whether it's the first one, the second one, the third one, the fourth one, the fifth one. Now in this case, they keep kind of marching gradually toward 1. So it makes it pretty easy to know that this is the next one, this is the next one. So even though they didn't write anything, it's an easy conclusion that the one that comes right next to it, this one, is going to be a sub 5. Now this was just a characteristic of this particular sequence. In other sequences, you might see that it dances around a little bit more wildly. So this style of notation might make it difficult to guess what the next one is going to be. Because they're just kind of dancing around, kind of alternating, and there might be a case where it's converging towards something, right? They're slowly marching toward a particular value, or they might not be, right? It might not converge to anything. So this style, I think, is a little messy, can be a little messy. So personally, and I think most people do, prefer this one. Okay, so this style of graphing in a two-directional or two-dimensional grid here, we have a vertical and we have a horizontal, and the horizontal is now going to be the integer values, and then the vertical value is the actual values in our sequence. So this becomes the ordered pair 1, 1/2. So this is 1, 1/2 is that point, and 2, 2/3 becomes that point, and so on and so forth, right? So we can visually see or approximate that this is a half, that this is 2/3, and so on and so forth. But it makes it easy to see where the sequence is approaching, right? So from this graph here, we can easily see that it's getting closer and closer and closer and closer to 1, right? Again, going back to Desmos, let's see, let's get rid of, so then back to Desmos, we can see that if this is y equals to 1, we can see that, let's get rid of that, the dots are getting closer and closer and closer to that blue line. Now let's make a few more dots. So 5, 6, 7, 8, 9, 9, 9, 9, 9, 9. So you can see that you're getting closer and closer and closer and closer and closer to the blue line, right? This is with just n going from 1 through 17. But really we want to think about what happens as it goes out to infinity. Right? So we can easily see that from here. It's approaching 1. Okay, note that since the sequence is a function whose domain is the set of positive integers, its graph consists of isolated points of coordinates a comma a sub 1, 1 comma a sub 1, 2 comma a sub 2, so on and so forth. Okay, we've already seen that. From figure 1 or figure 2, it appears that the terms of the sequence a sub n equals to n over n plus 1 approach 1 as n becomes large. In fact, the difference, okay, so if we subtract the difference between 1 minus n over n plus 1, we get 1 over n plus 1, right? So in other words, all you have to do is multiply the numerator and denominator of this by n plus 1 over n plus 1, right? And then if we actually subtract them, we'll end up with n plus 1 minus n all over n plus 1, which means these guys cancel, giving me 1 over n plus 1. And we could see that the limit as n approaches to infinity of 1 over n plus 1, as n gets larger and larger and larger and larger, right? At infinity, when this goes to infinity, it equals to 0, right? So the gap, the distance between the two values is getting infinitely smaller. So the difference can be made as small as we like by taking n to be sufficiently large. We indicate this by writing that the limit as n goes to infinity of 1 over n plus 1 equals to 1. And in general, the notation is the limit as n goes to infinity of a sub n equals to L means that the terms of the sequence a sub n approach L as n becomes large. Right? So remember that there's this weird duality with limits where if we stop at any specific point, then we don't have all of it yet. But if we think about the limit as it goes to infinity, then eventually this will be sort of all of it. The classic example to always go back to is that pie thing, right, or the cake, or whatever you want to call it. So let's say we have one whole cake, and on day 1, you eat half of it, right? You eat half the first day. And then on day 2, you eat half of what you have left, which means you really only eat 1/4. 1/4. And then the day after that, you eat half of what you have left. So then really you eat 1/8. Right? So as you keep going, you have this pattern where you eat a half, and then the next day you ate a 1/4, and then the next day you ate an 1/8, and then the next day you're going to eat a 1/16, and then you're going to eat a 32nd, right? So we start to establish this infinite sum here. And we're going to get to sums in a little bit, right? So if I decide to add all of these things together, eventually they're going to add up to 1 because there's only one pie. If I stop at any one point, then I haven't eaten all of it yet, so I can get infinitely close to eating all of it. I can get really, really, really close. I can get very, very close depending on how many days go by, right? So this is day 1. On day 1, I ate half of it. On day 2, I ate a 1/4 of it. On day 3, I ate an 1/8 of it. And then there's day 4, day 5, day 6, day 7. So no matter how far I go into it, whatever day nth one you want in here, the slice is going to get really, really, really small, but the slice is never going to be 0. There's always going to be like a little gap left. There's always going to be some amount left over if I stop at any specific value. But as I go out to infinity, in an infinite number of days, we can clearly see by the picture that the whole thing has to add up to 1. Right? Okay, so when we look at this, if we let n stop at any specific value, then we're not going to get quite to 1. We're going to get really close, but never quite exactly 1. But once we think about the limit as n goes to infinity, then that equals to 1. Right? It's not an approximation of 1. It's exactly equal to 1. Good? Good, good, good. If you have like a little brother or nephew or something that's turning 1, right, on their birthday cake, here's their birthday cake, we can write happy limit as n goes to infinity of n over n plus 1 day, and that equals 1. He's turning 1. Good, 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 good. Okay, so in general, we can say that the limit is capital L. That's the notation style we like to adopt to indicate if this limit exists as n goes to infinity. Notice that the following definition of the limit of a sequence is very similar to the definition of the limit of a function at infinity. So the sequence a sub n has the limit L, and we write that the limit as n goes to infinity of a sub n equals to L, or we also like to write this style. I think this style is a little less popular with people, but either one is good. If we can make the terms a sub n as close to capital L as we'd like by taking n sufficiently large. If, okay, so there's a little mistake here. So this is if n goes to infinity of a sub n exists, right? So if the limit as n goes to infinity of a sub n exists, we say the sequence converges, or is convergent. Otherwise, we sequence diverges, right? So if it doesn't go to any specific value L, it doesn't get infinitely close to some constant L, then it diverges. So here's some graphs kind of illustrating that. So what we have here is some graphs that illustrate some sequences. So we can maybe imagine that this is the first one on the list, right? We plug in 1 into our function, and this is the output. We can also say that this is the ordered pair 1 comma a sub 1, and this is 2, and this is 3, and this is 4, and so on and so forth. So this is a sub 1 is right there, and this is a sub 2 is that guy, and so on and so forth. Okay, so here's my sequence. It begins there and looks like it's climbing up, and then it kind of reaches a max and then begins to come down, come down, come down, come down, come down. And from here I could see that eventually the little dots are getting infinitely close to this horizontal line, capital L. So as n goes out to infinity, I can make these little guys get infinitely close to L. Right? There exists a value, a point, such that beyond that point, all the little output values, a sub n values, can get infinitely close to capital L. Right? So here we have a case where they cross from below above capital L and then get infinitely close to it. Here we have another graphical example of the same thing, except it looks like maybe it's kind of oscillating above and below it, above and below it, above and below it. But it still seems like it's getting closer and closer to capital L. So in both of these cases, we say that as the little a sub n values get infinitely large, they get infinitely close to capital L. Okay, so here's a more precise definition of what I was trying to explain there. So the sequence a sub n has a limit L, and we write that the limit as n goes to infinity of a sub n equals to L, or a sub n approaches L as n approaches infinity, if for every epsilon greater than 0, there is a corresponding integer capital N, such that if lowercase n is greater than capital N, then a sub n minus L is within epsilon. What does that mean? Okay, so let's say that there is some function a sub n given, right? Some given function of n. And you want to show that the limit as n goes to infinity of a sub n equals to, I'm just making some number up, 7. Here it is, okay? So if we graph this thing like this, let's say we have L equals to 7, that means we have this horizontal line here at y equals to 7, right? That's the equation value. Okay, so I didn't actually give you an equation for it. I'm just giving you a visual of what it would look like. So if it's true that the limit as n goes to infinity of a sub n equals to 7, and you're trying to convince that to somebody, it means that they will choose an epsilon value. Traditionally, typically, something really small. They want to be able to think of a gap surrounding L that's going to be my epsilon. So let's say that they choose epsilon equals to 0.5. ¿Qué está tocando? Oh, ¿tu iPad estaba tocando? ¿Tu iPad toca?
Mi iPad, yeah.
That's weird. Yo no sabía que iPads tocaban. Epsilon equal to 5. Okay, that means that this guy here is going to have a width of 0.5, and then above and below it, 0.5. So we're going to go up to 7.5. So we're going to have this line above it. That is the line y equals to 7.5. And then below it, we're going to go down a 0.5. So this would be the line y equals to 6.5. So then here come my a sub 1 values. Maybe for the first one, then a sub 1 might have been like right here. And then maybe a sub 2, maybe 2 jumps way over here. A sub 2 is over there. Maybe a sub 3 is right here. A sub 3. Okay, but then maybe the one after that, maybe it's over here. 4, a sub 4. Okay, so what we want to do is we want to find a value, capital N, so that every lowercase n value, every counting number bigger than that, results in an output value, a sub n, that is within this band. So let's say that after a sub 4, then the next one is here, a sub 5, then a sub 6, and then a sub 7, and then a sub 8. So that beyond that point, beyond this value, let's say we pick this capital, well, it becomes this one, say. Here is n equals to 5. We would say that if n is greater than or equal to 5, or n is greater than or equal to capital N, right, because we're letting capital N equal to 5, then for every counting number beyond that, when we evaluate it into our function, it's inside that band. So we need to figure out that this is the one that matches that one. Okay, and then this is just an arbitrary choice of what it would take to convince this person that these values are getting infinitely close to 7. Okay, but that was just an arbitrary choice. Maybe somebody else says, you know what, that's too wide. Let's make it a stricter restriction here. Let's say that I want to be convinced, let's say that I want to be convinced when this equals to 0.01. Now we're talking. Now it's going to be really, really thin. So now we want to go over here and say, no, this needs to be even stricter. Let's make this 0.01, really, really thin, which means that this guy doesn't go out to 7.5 and 6. So that means that this is only going to go up to 7.01. and this is going to go down to 6.99, right? So now that's a very narrow band. So because it's a very narrow band, in reality, this thing gets, gets a little closer and this gets a little higher. I just don't want to do that because then it'll be even harder to draw. Well, okay, let's just draw it. So that means that this guy is going to come right in there, and then this guy is going to come right in there. Okay, so we've made the band a little bit thinner, so now it might not be good enough to stop there, right? Because now there's some numbers that are outside that band. So I might have to go out farther along, maybe n, capital N equals to 10 now. Maybe something like that will be the place where it's good enough so that beyond that point, all the little dots, all the outputs of my sequence are inside that thinner band. Right? But again, we keep going. We don't want to let this be any constant number. It represents any positive number that is as small as possible. It could be 0.000000001. It doesn't matter how small it is. There will always be a capital N such that this will be true. Right? If we have a situation like that, then that's what we want to visualize when we want to think about this definition of a limit existing. Right, there's a nice little applet for that. Okay, so here we have the sequence 1 plus 5 sine n over 3 divided by the square root of n. Okay, so here's that sequence, and then you can see that these are the values. So when n equals to 1, we would end up with 1 plus sine of 1/3 divided by the square root of 1. And then that's what this is, the value of that. And then the second one, the third one, the fourth one, the fifth one, the sixth one, so on and so forth. Okay, so somebody chooses the epsilon. So let's say the epsilon is nice and wide. They think 2, right? Their threshold is a 2. There it is. So epsilon is a very wide band. So even starting, see they fail there, they fail there. Even starting there, starting at n equals to 6, all the other values from n equals to 6 forward, they will all be inside the band where epsilon equals to 2. Right? So that person is convinced. Then a new person comes in and goes, you know what, that width is not wide enough. How can I confirm that this sequence is going to converge to 1 with such a wide band? Let's make the band even thinner. Let's squeeze it down to 1. Let's make it 1 there. So you see now there's going to be more values that fail. So all of these fail to be within that band, and then a few of them are successful, but then we have some more values that fail, and then we have some that are successful, and then we have some that fail. But see, starting at this point forward, starting right there, this point forward, every single one of the values is inside that band. So now, when epsilon equals to 1, capital N equals to 25 becomes our solution. When lowercase n is bigger than 25, equal to or bigger than 25, every single one of these values is within that width. Right? Okay, well, somebody says, okay, 1 is not enough. Let's make it even smaller. Let's make epsilon equal to 0.5. Okay, so now n equals to 25 doesn't cut it. It no longer cuts it, right? These all fail to be inside that band, and then I have a few that do work, but then some that don't work, and then a few that do work, but then some that don't work, and some that do work, and some that don't work. So I have to keep going until I get to a point where all of them are going to work. So I might have to go out quite a bit until I get to that point. Almost there. And I think this is it right there. Right? When n equals to 100, looks like 99 doesn't work. It's like 100 is going to work. Starting at 100 forward, they start to all be inside that band. right? And so you can see that no matter how small epsilon is, I can always find a place that goes so far out that all the points in my sequence beyond that point are going to be inside my width. So we want epsilon to be some arbitrary value, which is very, very small. And as long as we can always find a corresponding value of capital N, such that the sequence is always within epsilon of the limit L, then we've proven that the limit does exist. All right, so hopefully that visual helped. Right? A sub n minus capital L is the distance between the a sub nth value and capital L. And we want to say that that distance is within epsilon. Okay, all right, moving on. I'm not a huge fan of this style of notation. We saw this before where we're graphing the values in our sequence on a single horizontal line. Notice that here is one where they don't quite go in order, so you have to pay attention. This is the first one on the list, and then it skips and goes to the second one, then the third one, and then the fourth one is way over here, and then the fifth one, then the sixth one, then the seventh one, then the eighth one's way over here, then the ninth one. All right, so it's kind of dancing around, but it looks like eventually it begins to isolate close to L. And so if we go within epsilon of capital L, right, so capital L plus epsilon, capital L minus epsilon, we can come up with a bound, a lower bound and an upper bound, such that all the values of our sequence beyond capital N are all inside these parentheses. Right? It's the same idea as in a two-dimensional grid. I think it looks a little better there. Right? So this is what we were just doing in the applet. Right? So someone is going to choose the epsilon, right? You're playing this game to convince them. You're like, okay, how close do you want me to be to L? So that person chooses epsilon, right? So that's this distance right here. This little gap right here, this is epsilon. Well, and so is this. They choose epsilon. It's 0.1, it's 0.01, it's some small, tiny little number. And once they've chosen that small, tiny little number, then it'll be your job to figure out a capital N that is so large or big enough so that all the other little n values that are going to be bigger than this one, so that when n is bigger than capital N, that all the little sequence values beyond that are going to be within epsilon of it. So if you play this game back and forth where every time they pick a number, you can figure out a value capital N, right? If that's true, you can always do that, then you've proven that the sequence converges to L. Right? Okay. So you will see that the only difference between the limit as n goes to infinity of a sub n equals to L and the limit of x approaches to infinity of f of x equals to L is that n required to be an integer. Thus, we have the following theorem, which is illustrated in this figure. Right? So remember, the only difference between these two is that here x is a real number. X is an element of the real numbers, whereas here n is an integer value. Sometimes we use capital I to mean integer. Sorry, it's a natural number, counting number. So n equals to 1, 2, 3, dot, 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 dot. Right, so that's really the only difference between these two functions. So here, the continuous red graph is the f of x, whereas the individual little points on that graph are the a sub n values. Okay, so we have theorem 3. If the limit as x goes to infinity of f of x equals to L, right, if the red continuous line converges to the line L, and f of n equals to a of n, right, so that means that each individual little dot for that represents the a sub n sequence is a value on that f of x function, when n is an integer, then the limit as n goes to infinity of a sub n equals to L. Right? So if the continuous red line is converging to the blue, then that means that the individual dots, right, if we can strip away the continuous line and just look at the dots are also going to be converging to the same place. That's what this is telling us. That's going to be very useful in this section. This is a very useful theorem. Right? So we don't have to reinvent the wheel. Everything we know about the continuous functions can be interpreted to the cases where we're only looking at sequences. In particular, since we know that the limit as x goes to infinity of 1 over x to the r power equals to 0 whenever r is a value strictly greater than 0, we have that, then we can convert that to the case where we have integer values. So the limit as n goes to infinity of 1 over n to the r power also equals to 0 if r is strictly greater than 0. Right? So again, the difference is that here x is a real number, whereas here n is just counting numbers. And remember, r is any number that's strictly greater than 0. Right? So what is this telling me? This is telling me that if I'm staring at this, the limit as n goes to infinity of 1 over n to the power of 3, and I'm thinking, what is this? What is this? Okay, well here r equals to 3, right? There's just an example I came up with where r equals to 3, and this is saying that if r is strictly greater than 0, then this tells me that the limit must be 0. Right? So as these integer values get larger and larger and larger, and every time we input a new integer value, we cube it, well, of course, the denominator is going to be growing out of control, right? Getting larger and larger and larger. So 1 over a very large number is going to get really close to 0. Right? And that's going to be true. You know, the 3 was just an arbitrary selection. It doesn't have to be 3. It could be, I don't know, 7. Right? If r equals to 7. R equals to 7. We'd have the same case. Nothing special about 7. Also, it could be that r equals to 1.2. Right? The r value is allowed to be a decimal, 1.2. We're still going to have something that converges to 0. As long as r is strictly greater than 0, this is true. Okay, so if a sub n becomes large as n becomes large, we use the notation that the limit as n goes to infinity of a sub n equals to infinity. Right? So this is how we represent that the sequence is not growing toward any particular value. It's not converging. It's just growing out of control. It's getting larger and larger and larger, and it never stops growing. So then this is the notation style we choose. Right? By definition, this means that for every positive number m, right? So anytime you choose a value m, there is an integer value, capital N, such that if lowercase n is greater than n, then a sub n is greater than m. Right? So visually, we want to say that if we have a case where the little dots, maybe they start here, and then they go there, and then they go there, then they go there, right? So they're kind of growing out of control. We want to say that the sequence is going to go toward infinity if it's true that anytime you pick an m, like say here, like here's capital M, there exists a lowercase value, I'm sorry, a capital N, say here's capital N, such that whenever n is greater than capital N, lowercase n, that all these subsequent values beyond that are going to be greater than that m value, right? No matter how big you choose it. Like, okay, well, let's make n even bigger. Like, okay, how about way over here? Let me say not there. M used to be here. You're like, not there. Let's make it there. Right? So m is chosen by someone you're trying to convince that the sequence goes to infinity. They're like, I'll be convinced if you can show me the sequence is bigger than this huge number, right? We're imagining these capital M numbers to be really big. Maybe this is a billion, this is 25 trillion. If you can show me that the sequence goes above 25 trillion, then I'll believe you. Like, okay, well then this n was no longer good enough. But then if you look at the sequence, okay, the sequence goes there, there, and eventually there is a point way over here. Here's my new capital N. And this capital N exists such that for every lowercase n that's greater than that value, all the resulting values of our sequence are going to be greater than that m, right? The m is here. So no matter how big that capital M is, we can always find a capital N such that all the values of my sequence are bigger than that. If that's true, then we've shown that the limit of a sub n goes out to infinity. Notice that there could be this weird case where they oscillate in a way that might be a little misleading. For example, it could be that these things oscillate this way, like maybe they go up, and they come down, and then they go up, and then they come down. So they could be kind of like doing this. And so maybe these oscillations continue to grow out of control, so that no matter how far away you go, there will always be a place where this is growing out of control like this. Let's use Desmos. This is really ugly. Let's see, Desmos. How about something like okay, so here's an example. X times sine x. Notice that it oscillates up and down, up and down, up and down. And so if n is chosen to be a big number, let's say n is 100, like, okay, can this function ever reach 100? Okay, here we can do that. Zoom out, zoom out, zoom out, zoom out, zoom out, zoom out, zoom out. And yeah, look, it reaches 100. Like, okay, I'm not convinced. Does it ever reach 1,000? Sure, it can reach 1,000. Oh, come on. It can reach 1,000. Let's go out this way. And you see that eventually this thing reaches 1,000. Can it reach 1,000,000? Yeah. We can zoom out, zoom out, zoom out, zoom out, zoom out, zoom out, zoom out. Let's see if this goes faster. Okay, I'm not sure if this is going to let me reach 1,000,000. I think I might have overreached there. But you see the point. No matter how big, let's say we said there, 10 is at 100,000. Reach the 100,000. So no matter what value I choose, it can always go past that value. But it's really oscillating, right? I know it looks solid, but it's not solid. We saw that when we zoom in, it's actually oscillating up and down. So it's actually oscillating up and down. So this fails the definition of the limit going out to infinity, because there isn't a point where every single value beyond that will be above m. Right? If we pay attention to the definition, the limit as n goes to infinity of a sub n equals to infinity means that for every possible positive number m, there is an integer n such that if n is greater than n, then a sub n is greater than m. Right? So in my little case, in my little example, f of n, I had n times sine of n. So the sine of n is what made it oscillate and caused that whole oscillation thing. And this is growing. But no matter how big a capital M is chosen, m is equal to, say, 1,000, we chose that value, there is a value capital N such that at least some of the values right? There is a capital N such that when lowercase n, sorry, the other way around, when lowercase n is greater than that value, there will be some that work, but there will always also be some that don't work. Right, so let me draw what I mean by that. So let's say I had this thing. So if I was only looking at the individual dots of that sequence, right, they go like this, and they go like that, and then they go like that. These are the individual values, and so the oscillations get wider and wider and wider, but it's always oscillating. So if we choose a value of, say, 1,000, so here is capital M equal to 1,000, you're like, okay, here is a successful one, here's a successful one, here's another successful one, but then there will be some that fail. So even if we choose capital N to be right there, there will be some that are successful, but then some begin to fail, right? And you're like, okay, well, let me choose a different value for capital N. If I choose capital N to be farther out, let's say over here, capital N, right? Yeah, okay, maybe that'll be true. Eventually, these little integer values go above that, right? So there will be some places where it's successful, but this thing keeps oscillating. So eventually, there will also be some values of a sub n, where a sub n is greater than capital N, right? There will exist some value way over here that is below that line, right? So here is a case where there is always going to be a number, lowercase n, bigger than capital N, such that the output of my sequence is greater than capital M, but there will always also be a number that is below that. So the limit is not equal to infinity, right? So in this case, this is a case to show that the limit as n goes to infinity of n sine n does not equal infinity. Okay. Good. Okay. We'll see some examples in a second from the homework and see how we can apply these things. Okay, laws of sequences. These are useful applications of laws of sequences, and again, in the homework, we'll see how we can use these. So if we have the sequence A sub n and the sequence B sub n are convergent sequences and C is some constant, then we have that the limit as n goes to infinity of A sub n plus B sub n is equal to the limit of A sub n goes to infinity of A sub n plus the limit as n goes to infinity of B sub n, right? So we can separate this summation in, the limit of a summation is equal to the summation of limits, right? So the limit of a difference is equal to the difference of limits, right? And then if we have a constant, the limit of a constant times A sub n, we can factor out that constant, and it's equal to the constant times the limit of the sequence. Good. And also, we know that if we have the limit of a constant C, there is no n, then it's just always equal to C. Good. If we have a product, A sub n, B sub n multiplied, and we want the limit of a product is equal to the product of limits. Right? So we can separate it into two separate limits, find them separately, and then multiply our answers together. Same thing with a division. The limit of a division, the limit of a quotient, is equal to the quotient of limits. We can divide them this way. Divide and conquer. Figure out the limit of the numerator, figure out the limit of the denominator, divide them, so long as, we always remember, we're not allowed to divide by 0. So as long as the limit of the denominator doesn't equal to 0, this rule applies. Good. And then if we have the limit of A sub n being raised to a power, then we can find the limit of A sub n and then raise that to the power of p. And this is so long as p is positive and A sub n is strictly greater than 0. Good. Okay, so we'll see some homework problems and we'll see how we can apply these limits. The squeeze theorem. The squeeze theorem for sequences. So if it's true, if we can establish a relationship between A sub n, B sub n, and C sub n that satisfies this, right? So these problems are very useful when we're trying to figure out the limit of b sub n, and we can establish that for any integer value n, it's always true that it's trapped between a sub n and c sub n. And if we can figure out, if we know that the limit of a sub n and the limit of c sub n are both equal to each other and they both go toward capital L, then we can conclude that the one that's stuck in the middle must also converge toward capital L, right? So visually we can see it here, where for any individual value n, it's always true that the a sub n1 is below, the c sub n is above, and the b sub n is somewhere in the middle. Sometimes it's close to the c sub n, sometimes it's close to the a sub n, but it's always stuck in the middle. And so if the limit of the lower one and the upper one converge to the same value, and that same value is L, both limits exist and they both converge to the same thing, then we can conclude that the one that's stuck in the middle must also go in the same direction. Again, we'll see some homework problems like this. Theorem 6. So if the limit of n goes to infinity of the absolute value of a sub n equals to 0, then the limit as n goes to infinity of a sub n equals to 0. Okay, so this is useful when we have some sort of a limit where this might alternate signs. This might be negatives or negatives and positives, right? So there's some negatives that are part of this sequence. And so this is saying, well, let's strip away the negatives for a second. Let's apply the absolute values and ignore the fact that some of the terms or all of the terms are negative. If we can show that limit of the ones that are all positives converges to 0, then we can say that the one that did have some negatives in the sequence also converges to 0. Good. The following theorem says that if we apply a continuous function to the term of a convergent sequence, the result is also convergent, right? So this one's very useful. So if the limit of n goes to infinity of a sub n equals to L, and the function f is continuous at L, then the limit of the function evaluated at a sub n, the limit as n goes to infinity of f of a sub n is equal to f of L, right? So what is this saying? For example, let's say that we have some sequence. Let's say given that there is some sequence and the limit as n goes to infinity of that sequence, let's say it equals to 7, right? Let's say we know that that's true. And we're trying to figure out what is the limit as n goes to infinity of, let's say, something squared a sub n like this. Well, if we think of this function as the squared function, f of x equals to x squared, this is continuous at 7. So because this is true, then this is going to be equal to 7 squared. Right? That's what this is saying. The f function is continuous at L, then that's the same thing as finding the limit as n goes to infinity of f of a sub n is equal to just plugging in an L into the f function. Okay, all right. Again, we'll see some examples that use that. The sequence r goes to n is convergent if r is between -1 to 1, and note that it is not inclusive of -1, but it is inclusive of 1, and divergent for all other values of r. Okay? So we can kind of combine that into this little statement. The limit as n goes to infinity of r to the nth power equals to 0 if r is between -1 and 1, and equals to exactly 1 if r equals to exactly 1. A sequence a sub n is called increasing if a sub n is less than a sub n plus 1 for all n greater than 1. Right? So that means that the actual values on my sequence keep getting larger and larger and larger. I think that's pretty intuitive. And the sequence is decreasing if a sub n is bigger than a sub n plus 1. and so on and so forth, right? So the numbers, the values on our sequence are getting smaller and smaller and smaller. A sequence is monotonic if it is either increasing or if it is decreasing, right? A sequence that is either increasing or decreasing is called monotonic. A sequence A sub n is bounded above if there is a value capital of n such that every value in our sequence A sub n is less than or equal to capital M, right? It's bounded above. It is bounded below if there is a lower m such that every value in my sequence is greater than that lower m value for n greater than or equal to 1. So if it is bounded above and below, then the sequence is said to be a bounded sequence. Right? If it is bounded above and below, then it's just bounded. For instance, the sequence A equals to n is bounded below, right? But not above. They just keep getting larger and larger and larger, right? N equals to the counting numbers out to infinity. The sequence 1 over n plus 1 is bounded because A sub n is always trapped between 0 and 1. Starting with n equals to 1, the first value in this list is a half, right? So notice that when n equals to 1, this was 1/2. When n equals to 2, this was 2/3, then 3/4, then 4/5, and so on and so forth. So the largest value was a half, right? So we can just say 1. It's bounded above by 1. And it's bounded below by 0 because this gets closer and closer and closer to 0, but it's never actually going to be equal to 0. So it's bounded by these two values. Bounded above, bounded below, so we just say the sequence is bounded. We know that not every bounded sequence is convergent, right? So it could just oscillate back and forth, back and forth. For example, A sub n equals to -1 to the nth power. That's just going to alternate between -1 and 1, -1 and 1, -1 and 1. So it's bounded, but it's never going to converge to anything. But it is divergent, and not every monotonic sequence is convergent, right? Monotonic just means that it's either increasing or decreasing. So just the sequence A sub n equals to n, we see that just grows out of control, so it doesn't converge. However, when you bring those two together, a sequence is both bounded and monotonic, then it must be convergent, right? So if it's bounded, right, bounded above, bounded below, and it's monotonic, it's either increasing or decreasing, then we can conclude that it must converge. Right, so here is an example. This fact is proved as theorem 12, but intuitively you can understand why it is true by looking at this figure. So if A sub n is increasing, right, so here the little dots are increasing, right? They're getting larger and larger and larger and larger and larger. So here the sequence is increasing, and it's approaching some value, capital L. So M could be an upper bound. Right? All the little dots are definitely below capital M, and they are increasing. So therefore, it is we can conclude that the sequence is going to converge. Right? So every bounded monotonic sequence is convergent. All right, let's look at some examples from your book. Okay, so here are the homework exercises for section 1 in chapter 11. So let's just take a look at a few of these. 3 through 12, list the first 5 terms of the sequence. That should be really easy, right? Let's just take a couple of these. Say, for example, number 4. This is chapter 11, section 1, number 4. And it has the sequence A sub n equals to n squared minus 1 all over n squared plus 1. Okay. And so again, the instructions were to list the first 5 terms of the sequence. Too easy, right? Okay, so n equals to 1. So then that'll be 1 squared, blank squared minus 1, all over blank squared plus 1. That'll be the first term. N equals to 2. That'll be blank squared minus 1 all over blank squared plus 1. That'll be the second one. N equals to 3. Blank squared minus 1 over blank squared plus 1. N equals to 4. It'll be blank squared minus 1 over blank squared plus 1. And then n equals to 5. Blank squared minus 1 over blank squared plus 1. Okay, so n equals to 1, 1 squared minus 1, 1 squared plus 1, n equals to 2, 2 squared minus 1, 2 squared plus 1, 3, 3, 4, 4, 5, 5. Okay, so we have that the first one is 1 minus 1 is going to be 0. It's going to be 0 over 2. And then this one's going to be 4 minus 1 is 3, all over 4 plus 1, which is 5. And then the next one's going to be 9 minus 1 is 8 over 10, 9 plus 1. The next one's going to be 16 minus 1 is 15, divided by 17, 16 plus 1. And then 25 minus 1 is 24, all over 25 plus 1 is 26. Okay, so we could leave it like this, but then we can also reduce some of these, which might make it a little more confusing. So if we reduce this, this becomes 4/5. Divide by 2, divide by 2. And then reduce this one, that's going to be 12/13. 12/13. So our final way of listing this could either be just the sequence 0, right? This is just going to be 0. I could just list them as 0, 3/5, 4/8, 15/17, 12/13 as the first 5 terms, right? Or we can also list them by putting that a sub 1 equals 0, a sub 2 equals to 3/5, a sub 3 equals to, oops, sorry, not 4/8, 4/5. 4/5 from there, 4/5. 4/5, comma, a sub 4 equals to 15 over 17, and finally a sub 5 equals to 12 over 13. Okay, so the first couple are pretty easy. We just replace n with 1, 2, 3, 4, and 5, and eventually get the first 5 terms of the sequence. 9, 10, 11, and 12 are recursive sequences, so they are defined by the values that came before it. Right? And so, for example, number 10 here says that to get the n plus 1th value on my list, we got to first figure out what the a sub nth value is, and then divide that by n. Right? And of course, you got to get the ball rolling. So let's look at number 10. Chapter 11, section 1, number 10. Chapter 11. So we get the ball rolling with a sub 1 equals to 6. And then we know that the next one on the list is going to be equal to a sub n divided by n. So we have the first one on my list as a sub 1 equals to 6. Okay, so to get the next one on my list, a sub 2 is going to be equal to a sub 1 divided by 1. Good. So a sub 2 is going to be equal to 6 divided by 1, or a sub 2 equals to 6. All right, the next one on my list, a sub 3 is equal to a sub 2 divided by 2, which means that a sub 3 will be 6 divided by 2. A sub 3 will be equal to 3. Okay, to get the next one on my list, start to see the pattern. A sub 4 is equal to a sub 3 divided by 3. So a sub 4 is going to be equal to 3 divided by 3, or a sub 4 equals 1. And finally, to get the 5th one, a sub 5, I got to go to a sub 4 and divide that by 4. So a sub 5 is going to be equal to 1 divided by 4. So a sub 5 is 1/4. There. So there's the first 5 terms. Good. So this is a recursive sequence. You always have to know which came before it. Just to go one more here, say I wanted to find the 6th one on my list. That would be the 5th one on my list divided by 5. A sub 6 would be equal to 1/4 divided by 5, which then would be a sub 6 equals to 1/4 times 1/5, or a sub 6 equals to 1/20. Good. Okay, so the problem with these, or the the limiting factor of these, is that you can't just jump to some value down the line. Like if I wanted to know was a sub 13, well, that's going to be equal to a sub 12 divided by 12. I need to know the value of a sub 12. So I can't just jump to the 13th value on this list. So you have to find them in order, starting from some place and find the next one, the next one, the next one, this one. So it makes it difficult to find some large value. Okay, so I don't think these are too bad. Moving on. Okay, find a formula for the general term of a sub n in the sequence. So find a formula for it. Okay, these can be a little tricky. They just take a little bit of practice. So let's see which one. Let's try. So if we see fractions, it's a good idea to separate them and try and establish some pattern. So for number 14, for example, the first thing that would pop out to me is that the 4, the 16, the 64, those seem to be powers of 2. So maybe that's a clue of something that has to do with powers of 2. And then the numerators, for the most part, are just going to be 1. They're going to be 1, and then they alternate signs. So it has something to do with alternating signs, and the denominator has something to do with powers of either powers of 2 or powers of 4. Chapter 11, section 1, number 14. So I have a 4 followed by a -1, followed by a 1/4, followed by a -1/16, followed by a 1/64, dot, 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 dot. Okay, my goal is to find some function such that when n equals to 1, the output is 4, and when n equals to 2, the output is -1/2, and when n equals to 3, the output is 1/4, and equals to 4, the output is -1/16. So the alternating signs, that seems like it's going to be something like this, or -1 to the n plus 1. Either one of these, depending on whether I want to start with a positive or a negative, so we'll play around with that to get the alternating signs part of it. So if the denominator is powers of 4, 2 to the 4th power, 3 to the 2 to the 3rd power, right? So powers of 2 would look like this. Well, 2 to the 1 power is 2, 4, 8, 16, 32, 64. So that's interesting that it's kind of missing out on some of these powers. Note that if we multiply the 4, the first term, times -1/4, that equals to -1. I guess to there. And if we multiply -1 times -1/4, that makes it +1/4. And if we multiply +1/4 times -1/4, that gets you to -1/16. And negative 1/16 times negative 1/4 is equal to positive 1 over 64. So it looks like from term to term, we multiply by negative 1/4. Right? Always multiplying by negative 1/4. Right? Okay. So we start off with this. So we have 1. So we have 4. And then we're going to multiply by various properties or various powers of negative 1/4. Let's just test these out. So if n equals to 1, this would end up with this one as the first one. So n minus 1 gives me 0 there, which would give me the first one there. Good. Because, so if this equals to 1, the power of 1, it's equal to that. But also notice that this is the same thing as 4 times negative 1/4 the power of 2. This is going to be the same thing as this. That's going to be, yeah, 1/4. And then this one is the same thing as 4 negative 1/4 the power of 3. Right? To go from here to here, we multiply it by negative 1/4. And then to go from here to here, we again multiply it by negative 1/4. So we can kind of rewrite this term in terms of the first one by saying it's this one multiplied by negative 1/4 twice. And same thing for this one. We can say that because at each turn we multiplied it by negative 1/4, this one can be written as 4, the very first term, times negative 1/4 once, that got me to negative 1, times negative 1/4 twice, that got me to positive 1/4, times negative 1/4, that'll get me to negative 1/16. And all of that can be rewritten as negative 1/4 to the power of 3. Okay, so we have our sequence there. So it's a combination of guessing and checking and trying different things. Always look for patterns where you're multiplying by some constant number, or you're always adding some constant number, or if you want to separate it into a pattern for the numerator, a pattern for the denominator, and approach it that way. See number 16, for example, this one's an easy pattern where I'm always adding the same amount, plus 3, plus 3, plus 3, plus 3, plus 3. Right? So number 14 was a case where I was always multiplying by the same amount. Whereas 16, it's a case where I'm always adding the same amount. And 18 is going to be a similar situation. 1, 0, negative 1, 0, 1, 0, negative 1, 0. Okay, so looking at number 16. Chapter 11. Section 1, number 16. 5, 8, 11, 14, 17, 14, 17. Here's my sequence, dot, 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 dot. Pattern is established. So now we want to figure out a formula so that when I plug in n equals to 1, the output is 5. And when I plug in n equals to 2, the output is 8. And then n equals to 3, the output is 11. And I can see that all I'm doing from there to there is that I'm going to add 3, and then add 3, and then add 3. Good. So it's something like 5. The 8 can be thought of as 5 plus 3. And the 11 can be thought of as 5 plus 3 plus 3. Right? It's like 5, and then it's 5 plus 3. And then it's 5 plus 3 plus 3. And then the one after that would be 5 plus 3 plus 3 plus 3. And then dot, 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 dot. Okay, so we can also think of this as 5 and then 5 plus 3, and then 5 plus 2 copies of 3, and then 5 plus 3 copies of 3, and then it's going to be 5 plus 4 copies of 3, and so on and so forth. So we can see a pattern here, and well, just to complete that pattern, I'm going to come back and erase this one and change it to 5 plus 1 copy of 3, and we can see this little counter here, 1, 2, 3, 4. So then just to make it super complete then, let's erase this guy here and say it's 0 copies of 3. So this will be 5 plus 0 copies of 3. Right, and now we have that little counter. Okay, so if I let this be my formula, at this point I can think of 5 plus n times 3. But then n equals to 0 would be that first one there, and then equals to 1 would be the second one. But that's not what I want. I want n equals to 1 to be the first one. So I want to fudge this a little bit and rewrite it as 5 plus, and then let's make it n minus 1 times 3. That way when n equals to 1, I really get a 0. When n equals to 2, I really get a 1. Right? So then that will match up with this. When n equals to 0, when n equals to 1, we get a 0 there. When n equals to 2, we get a 1. When n equals to 3, we get a 2, and so on and so forth. So this becomes my formula now. Right? A sub n equals to 5 plus n minus 1 times 3. Which means I can distribute and simplify things a little bit and say that a sub n equals to 5 plus 3n minus 3, which means a sub n equals to 3n plus 2. And then again confirm, when n equals to 1, we get 3 plus 2 is 5. Yep. When n equals to 2, we get 6 plus 2 is 8. Yep, that's what we wanted. So it seems to make sense, right? So just guess and check different things until you get to, a formula, and always verify that your formula really does go back and represent the original sequence. All right, so hopefully those are pretty good. Okay, 19 through 22, calculate the 4 decimal places, the first 10 terms of the sequence, and then use them to plot the graph of the sequence by hand. Does this sequence appear to have a limit? Okay, so I would recommend that you use a table, use some technology to figure these out, and we do have a nice place on our calculator to be able to do that. So let's say, for example, on number 20, 20 is going to be the following. So let's use technology to begin this process. So let's go to our Desmos. Let's get rid of that, get rid of that, get rid of that, get rid of that. Let's create a table, and let's call this n. And it was 2 minus, I think it was negative 1 power of n divided by n. Oh, it's plus 2 plus. Okay, 2 plus negative 1 to the nth all over n. And So let's see what happens for various values. Okay, when we replace the n with a 1, we're going to get a minus 1 over 1, which is just minus 1. So then we end up with 1. We'll end up with 2 plus negative 1, which gives you positive 1. Okay, when n equals to 2, then that means that this will be a positive number, and then we'll end up with a 2. This will be 2 plus a half, so 2 gives you 2.5. And then 3, and then 4, and then 5, 6, 7, 8, 9, 10. So here are the first 10 values. Let's zoom into here so we can see them. There they are. And as we can see, here is the first one, 1, 1, then 2, 2.5, then 3, 1.67, and then 4, 2.5. Looks like they are oscillating, just as probably we would have guessed, around the line y equals to 2. Let's change the color of that guy to red. Right? And that's because this is going to become positive, negative, so it'll oscillate between adding a little something to the 2 or subtracting a little something from the 2. Adding a little something, subtracting a little something, and that constant that you either add or subtract keeps getting smaller and smaller and smaller, so we're always kind of dance around and oscillate around this value of y equals to 2. Good. Okay, so that's what the problem is asking you to do. Calculate each one of these things by hand. I think it's a bit of an overkill to do 10 of them by hand. Technology would be good. You can also use your calculator to figure out these guys, and then you can see that you can kind of redo this by hand and get a pretty good graph. Okay, so I think that should be doable. That's the homework for those. Calculate to 4 decimal places the first 10 terms of the sequence, and then plot them. Okay, so that should be doable. What's next? 23 through 56. Here we go. Here's the bulk of our problems here. Determine whether the sequence converges or diverges. If it converges, find the limit. Okay, so we have this guy here. We need to decide if this converges or diverges, and if it converges, we need to find the limit. Okay, so for example, number 24, what could we do there? Okay, chapter 11, section 1, number 24. There. Has a sub n equal to 3 plus 5n squared all over 1 plus n. Okay, so we have this sequence, and we want to know what happens as n goes to infinity. To do that, we can apply this little trick. I'm going to multiply the numerator and denominator by 1 over n, 1 over n. And I'm motivated, inspired to do that because the biggest power here is n to the power of 1. Okay, and so now if I distribute that, I'll get that this new sequence will be equal to 3 times 1 over n plus 5n squared times 1 over n divided by 1 times 1 over n plus n times 1 over n. Okay, n over n will cancel, just to give you 1. We'll still have 1 over n there. Right? So they'll end up with a sub n equals to 3 over n plus 5n all over 1 over n plus 1. Okay, so now the limit as n goes to infinity of 3 plus 5n squared all over 1 plus n is equal to the limit as n goes to infinity of 3 over n plus 5n divided by 1 over n plus 1. And from our properties of limits, we know that if we have a limit of a fraction, we can turn that into the division of two limits. Let's break this down into figuring out the limit of the numerator, which is the limit of 3n plus 5n, divided by the limit of the denominator, as long as the limit of the denominator does not equal to 0, which it certainly will not in this case. Good. So now the limit of the denominator, well, this is going to go towards 0. We know that 1 over n is going to go towards 0. So let's break this down. This is going to be equal to the limit as n goes to infinity of 3 over n plus the limit as n goes to infinity of 5n divided by the limit as n goes to infinity of 1 over n plus the limit as n goes to infinity of the number 1. Okay, so the limit of a constant as n goes to infinity, well, this is just going to be 1. The limit as n goes to infinity of 1 over n, this is going to go towards 0. So in the denominator, we'll get 0 plus 1, which is just going to be 1, converges toward 1. This guy is going to go towards 0. The limit as n goes to infinity of 3 over n, that goes towards 0. And then this is going to get infinitely large, right? As n goes to infinity, 5 times n is just getting larger and larger and larger and larger. So the whole thing is going to go toward infinity. Right? And then that's going to be my final answer. The limit as n goes to infinity of the original one, which was equal to 3 plus 5n squared all over 1 plus n converges to infinity. So 3 plus 5n squared over 1 plus n diverges. All right, let's try another one. Something in the 20s. How about something in the 30s? 32. So cosine oscillates, and then we'll have this in the argument of the cosine function. So we'll have powers of pi increasing divided by this, the constant. So they're getting closer and closer and closer to pi. Okay, so let's take a look at number 32. Let's consider separating this. So consider n pi over n plus 1. Right, so let's consider this sequence here, b sub n equal to this for a second. Well, the pi is even a constant, so we could consider this. The limit as n goes to infinity of b sub n is equal to the limit as n goes to infinity of n pi over n plus 1. Well, this is just some constant. We can pull that out in front and say that this is pi times the limit as n goes to infinity of n over n plus 1. As n goes to infinity, we can also multiply the numerator and denominator by 1 over n. 1 over n divided by 1 over n. And so we would get that this is equal to pi times the limit as n goes to infinity of 1 over 1 plus 1 over n, which would then give you pi times the limit as n goes to infinity of 1 divided by the limit as n goes to infinity of 1 plus the limit as n goes to infinity of 1 over n, which then gives you a 1 divided by 1 plus 0. So we end up with just pi. Pi times 1, which just equals to pi. Okay, so we've established that the limit of, as n goes to infinity, of the inside part here converges toward pi, and we know that cosine is continuous, as a function is continuous at pi. So cosine of x is continuous at x equals to pi. So the limit as n goes to infinity of cosine of n pi over n plus 1 is equal to cosine of pi, which is going to be equal to -1. So that's our answer. The limit as n goes to infinity of cosine of n pi over n plus 1 equals to -1, therefore it converges. So it converges. (34) can be solved in a similar way. If we think about e to the power of x being a continuous function, and then we can find the limit of this exponent, and if that converges to a constant, and then the function is continuous at that value, then we can just evaluate it there. Right, so let me write down number 34. Okay, so now let's just take a look at the numerator. So let's consider the limit as n goes to infinity of 2n divided by n plus 2. So we can multiply the numerator and denominator again by this 1 over n divided by 1 over n, and that gets us to the limit as n goes to infinity of 2 divided by 1 plus 2 over n, right? And so now we can break this down into one giant fraction, where we have the limit as n goes to infinity of 2 divided by the limit as n goes to infinity of 1 plus the limit as n goes to infinity of 2 over n. So this is a constant, that's just going to be a 2. That's a constant, that's a 1. And then this goes towards 0. So we have that limit exists, and it's going to be equal to 2 over 1 plus 0, or just 2. Okay, so bringing this all together lets me know that the limit as n goes to infinity of 2n divided by n plus 2 equals 2. Okay, so now that we have that in mind, note that if we have the function f of x equals to e to the x, this function is continuous at x equals to 2, right, which is the exponent. Okay, so now that we're armed with all that, now we're ready. The limit as n goes to infinity of e to the 2n divided by n plus 2 is equal to e to the power of the limit as n approaches infinity of 2n over n plus 2, which is equal to e to the second power. Right? And that's our answer. Right, so we can just kind of eliminate that middleman there and just write our answer as the limit as n goes to infinity of e to the 2n divided by n plus 2 equals e to the second power, which means it converges. Okay, that should take care of those. Let's see, what else? What else is in your homework? Okay, so 31 through 37, and then 31 through 37. Okay, so those are the kinds of problems we just did. Then 39 through 44 all. Okay, so more of these. Let's try one like, say, number 42. Chapter 11, section 1, say number 42, has a sub n equal to ln of n plus 1 minus ln of n. Okay, so one of the properties of the ln function is that we can bring these two together and to be one big happy ln function if we divide these. Okay, and we know that if we have the limit of this guy, so the limit as n goes to infinity of n plus 1 over n, that's going to also be equal to, we do the same trick we've been doing so far. We do that, and we end up with 1 plus 1 over n all over 1. This is equal to the limit as n goes to infinity of 1 plus 1 over n over 1. And this will go towards 0. We end up with 1 over 1. So this whole thing is just going to be equal to 1. So the limit as n goes to infinity of this thing is equal to 1. And ln is continuous around the value 1. Note that if we had f of x equal to ln of x, that this is continuous at x equals to 1. Right? The graph of this thing looks a little something like this. Goes like that. Right? So right around 1, it's going to be close to 0. But it's continuous. That's all that matters for this to be true. Okay, so we have everything we need. Let's say then the limit as n goes to infinity of ln of n plus 1 minus ln of n is equal to the limit as n goes to infinity of ln of n plus 1 over n, which is equal to ln of the limit as n goes to infinity of n plus 1 over n. And that's true because this is equal to 1. It's equal to ln of 1, which is equal to 0. Okay, so then we could come back to our original. Right, the original question was asking about this. And so we could say that a sub n, well, not a sub n, we could say that the limit as n goes to infinity of ln of n plus 1 minus ln of n equals 0. So it converges. All right, let's take a look at number 46. That has an interesting property. 2 to the negative n times cosine n pi. Okay, so let's see. Does this converge or diverge? So chapter 11, section 1, number 46 has a sub n equal to 2 to the negative nth power times cosine of n pi. So as n grows to infinity, n equals to 1, 2, 3, I'm looking at multiples of pi. Cosine of 1 pi, cosine of 2 pi, cosine of 3 pi. Okay, so if we look at the cosine function, it starts off there, comes down here, hits that, comes back up there, comes back up there. So it's going to be equal to negative 1 for pi, and then it's going to become positive 1 for 2 pi, and then it's going to come back down, and it's going to come back up, and it's going to. So this is just going to be oscillating back and forth, back and forth, back and forth, back and forth. Now this part, right? I can also rewrite it this way: 1 over 2 to the nth power. So we can see that this is going to be getting smaller and smaller and smaller. So something that's getting smaller and smaller times something that's just going to be oscillating back and forth. Makes sense that it will eventually converge. So in order to prove that this is true, what we can use is we can use the squeeze theorem here. So I can say that this guy, so this one's alternating positive negatives, and we have a theorem that says that if we can figure out what happens to the absolute value of this and it converges to 0, then we don't have to worry about the fact that it oscillates, back and forth. I'm going to say that cosine of n pi divided by 2 to the n is always less than or equal to, the most that this can ever possibly be is a positive 1. So this is just trapped by 2 to the n. And then on this end, the least this could possibly be is a negative 1. So this is negative 1, 2 to the n. So if I think about the absolute value of this, absolute value of cosine of n pi over 2 to the n, absolute valued, well then it's trapped by that, but then since it's absolute valued, then it's got to be a positive, so it's trapped between 0 and this, 1 over 2 to the n. So now if we think about the limits, the limit as n goes to infinity of 0 is less than or equal to the limit as n goes to infinity of the absolute value of cosine of n pi over 2 to the n, absolute value, which is less than or equal to the limit as n goes to infinity of 1 over 2 to the n. Okay, so here, this is obviously 0. The limit as n goes to infinity of 0 is just going to be 0. The limit as n goes to infinity of 2 to the nth power, this is also going to be 0. So I have a case where the thing in the middle on a term-by-term basis is always, on a term-by-term basis, this guy's always in the middle. And then the 2, the limits exist, and they go out to 0. So therefore, I've concluded that this middle one must also be equal to 0. So now I've concluded that the limit as n goes to infinity of the absolute value of cosine of n pi over 2 to the n absolute value must be equal to 0. And we had one of our properties that said that if you can slap absolute values in there and show that the limit is equal to 0, then we can conclude that the limit as n goes to infinity without the absolute values, cosine of n pi divided by 2 to the n, must also be equal to 0. Let me show where that was. That's what this theorem was about. Where'd it go? 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 Right here. Right? So we're trying to show, if we're trying to show that a particular sequence converges to, that the limit as n goes to infinity of a sub n equals to 0, then if we can show that its absolute value, the sequence in absolute values, goes to 0, then we can conclude that the original sequence without the absolute values must also equal to 0. Right? This is exactly what we used to figure out this one. Okay, we're trying to figure out what happens to this thing as n changes from 1, 2, 3, 4. The values of this will oscillate between positive and negative, positive and negative, positive and negative. So in order to figure out how that converges, then I can think about its absolute value. Its absolute value is always going to be trapped between 0 and positive 1 over 2 to the nth power. So therefore I can conclude that this is true with absolute values, that's this. Therefore I can then conclude that this must be true. Determine whether the sequence is increasing, decreasing, or not monotonic. Is the sequence bounded? Increasing, decreasing, not monotonic. Is the sequence bounded? Okay, let's try some of these guys. Okay, let's take a look at number 74. A sub n equals to 1 minus n all over 2 plus n. And it says determine whether the sequence is increasing, decreasing, or not monotonic. And then is the sequence bounded? Okay, and then those two pieces of information can let you conclude whether the sequence is convergent or divergent, or not enough information. So let's see. Let's try. So chapter 11, section 1, number 74. We have a sub n equals to 1 minus n over 2 plus n. Okay, so how does this compare? I mean, you know, sometimes you might want to just try a few values to see how the sequence begins to progress. So if n equals to 1, we get 0 over 3, or just 0. If n equals to 2, we get negative 1 over 4. If n equals to 3, we get negative 2 over 5. If n equals to 4, we get negative 3 over 6. Okay, so I see a pattern. The numerators are 0, negative 1, negative 2, negative 3. So it'll be negative 4, negative 5, negative 6. Okay, the denominators seem to be growing 3, 4, 5, 6, 7, 8, 9. Okay, so this is just 0. And then 0.25, 0.2, 0.5. So this is 0. And then negative 0.25. And then negative 0.2. And then negative 0.5. And then seem to be marching. No, wait, this is 0.4. Makes more sense. 0.25, negative 0.4, then negative 0.3, and then 4 divided by 7. I get negative 50. Negative 0.5714, and then 5 divided by 8, I get negative 0.625. So it looks like they're growing toward the negative. Looks like they're growing toward negative 1. Looks like they're heading toward negative 1, right? I can also use Desmos to help me visualize this. Let's go back to Desmos, good old Desmos. And the formula is going to be, let's get back into this guy. It's going to be parentheses 1 minus n, close parentheses, divided by 2 plus n. Plus n. So yeah, it looks like it is heading toward negative 1, sorry. As I keep going, those values are getting closer and closer and closer to negative 1. Okay, so looks like it's decreasing, right? So it looks like for every, I think, a sub n, the sequence is decreasing, right? Just basing it on this, right? Remember on the number line, when values go 1, 2, 3, they go that way, that's increasing. So in that direction, it's increasing. So when values go 3, 2, 1 in this direction, they're decreasing. Right, so I have a case where here's negative 1, and the numbers are heading that way. They're heading toward negative 1. So I think they're decreasing. And if they're decreasing, that must mean that a sub n plus 1 is always less than a sub n, right? Because the next one is smaller than the one that came before it. That's the definition of decreasing. So let's confirm that that's true. So if this is true, it must mean that this guy is 1 minus n divided by 2 plus n, and that is always larger than, it must be true that over here, if we have 1 minus n plus 1, all over 2 plus n plus 1. Okay, now we can simplify that a little bit. Distributing, we end up with minus n divided by n plus 3 is less than 1 minus n over 2 plus n. Good. Now remember, n is equal to 1 or 2 or 3, dot, 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 dot. So not a 0 in the denominators, right? So the smallest this could possibly be is a 4, and then a 5, and a 6. And same with over here, it's never going to be 0. And it's also never going to be a negative in the denominator. And this is always going to be a negative in the numerator, right? So we have a negative. That's negative. Okay, so if we have a negative number is less than some other negative number, then we can multiply both sides by a positive number times a positive number times that same positive number, and we still maintain the inequality. So we're going to multiply this side. We have negative n over n plus 3 less than 1 minus n over 2 plus n. I'm going to multiply both sides of the inequality by 2 plus n, which is a positive number, times 2 plus n. And then I'm also going to multiply it by n plus 3 times n plus 3. Again, another positive number. So I'm multiplying both sides by a positive, so the inequality stays the same. Now here, these two cancel, and here, these two cancel. So what I end up with is 2 plus n times negative n is less than 1 minus n times n plus 3. Okay, so I can distribute these, and I end up with minus 2n minus n squared is less than n plus 3 minus n squared minus 3n, which is minus 2n minus n squared is less than minus n squared minus 2n plus 3. Okay, so I can always add 2n to this side plus 2n to that side. And I can always add or subtract positive or negative number and maintain the inequality, right? We only change the direction of the inequality whenever we multiply or divide by a negative number, which we're clearly not doing here. We can also plus n squared and plus n squared, and we end up with 0 is less than, now these guys cancel, and these guys cancel to get that 3 is greater than 0, which is always true. Right, so like all the n's disappeared, which means that this is always true. Always true for any value of n. Right, oh, well, of course, n was any value of n where n is 1 or 2 or 3 or dot, 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 dot. Right? It's important to point that out because here, when we multiplied both sides by this value, we were counting on them being positive values, so we didn't have to change the direction of the inequality. So that was important. Okay, so what have we done? We have shown that this is always true, which means that this is always true, which means that this is always true, means that this is always true. So following down the chain, we've established that this is always true. So we've established that this sequence is indeed decreasing. right? We've established because this is true, it must mean that this is true, that this is true, that this is true, that this is true, all the way back down, the fact that this is true. So we've established that the sequence is decreasing. Now, decreasing and bounded. Well, from our Desmos graph, we saw that, or we got the intuitive idea that this was heading toward -1. So there is a lower bound, and the lower bound doesn't have to be the -1. We can just pick anything below that. Lower bound is any value where all the values in my sequence are bigger than this one. So the lower bound could be anything like m equals to -2, for example, -2, or m equals to -7, right? Anything lower than -1 is a lower bound. But in particular, if we want to work with the limit as n goes to infinity of 1 minus n all over 2 plus n, then we can do the same old trick we've been doing so far, 1 over n divided by 1 over n. And so this is going to be equal to the limit as n goes to infinity of 1 over n minus 1 over 2 over n plus 1. And so this is equal to the limit as n goes to infinity of 1 over n minus the limit as n goes to infinity of 1 divided by the limit as n goes to infinity of 2 over n plus the limit as n goes to infinity of 1. So this will go to 0, this will go to 1, this will go to 0, this will go to 1. So we end up with 0 minus 1 all over 0 plus 1. Right, so this is equal to that. So this will be equal to 0 minus 1 over 0 plus 1, which then just becomes -1. Okay, so the limit converges to -1. So it's bounded below. It is decreasing. So I know that the sequence is going to converge. It's bounded below by -1, and it's bounded above by, well, all the terms are, except for 0, all the terms are negative, so it's bounded above by any positive number. So the sequence a sub n is bounded below, right? It's always greater than -1, and it's bounded above by any positive number, right? The biggest number could be a 0, but I could also just put a 1 there or a 2 there, it doesn't matter. It's strictly less than that, it's bounded. So we just use instead of just saying it's bounded below, we just say it's bounded. So a sub n is bounded. Right? It's a more powerful statement of saying it's bounded because it's bounded from above and bounded from below. It's just bounded. And we established that it was decreasing. And so because we know that a sub n is decreasing, and bounded, it didn't ask us this, but we can conclude that a sub n converges. All sequences that are bounded and monotone, right? The fact that it's increasing means that it's monotone, it's going in one direction, so it converges. All right, that should be enough to take care of the homework, I think.